Yeah, thank you all for coming. Today, I want to talk to you about site speed, in particular, a very specific subset of site speed. I want to talk about largest contentful paint. Largest contentful paint, or LCP, is one of three relatively new web performance metrics coined by Google as part of their Core Web Vitals initiative. And over the next sort of 30 to 40 minutes, we're going to learn way more than we ever wanted to know about LCP, what it means for websites, and most importantly, how to optimize it. My name's Harry, and I'm a consultant web performance engineer. What that basically means is I spend my day-to-day helping clients find and fix web performance site speed issues. Generally speaking, my clients are fairly large companies because they're the kind of people who would feel the benefits of site speed improvements more than others. But ever since Google announced their intent to factor site speed and page speed into their ranking algorithm, I found that a much wider and much more diverse array of clients have started getting in touch, which is great news for me, because diverse clients and diverse projects is just really exciting. But it's really helped to put site speed on the map. This is not going to be an SEO talk, just because I don't have the time. I would love to get into more detail about that. It's going to be mainly a technical talk, but if anybody wants to talk about the SEO implications of being fast, more than happy to do that over several beers. But let's start with just a definition. LCP. What is LCP? Largest contentful paint, like I said, is one of three relatively new web performance metrics coined by Google when they created their Core Web Vitals initiative. You may remember having used things like load times in the past as a very, very crude proxy for site speed. LCP is kind of an evolution of that user experience metric of how fast a site felt. And it is still a proxy, because what we're looking for is, technically, when was the largest bit of content, largest single bit of content painted to the screen? Now, the largest bit of content isn't necessarily the most important, so your mileage will vary. But it's a really good start. It's a good way of getting to the kind of the user experience feel of how fast a website is. The largest piece of content on a site is very, very subjective. It depends on the site in question. And one thing I learned about 45 minutes ago is that Øredev website, the LCP candidate is actually this H1 here, sort of. This was about 45 minutes ago. I was like, oh, I'll put an Øredev screenshot in my presentation and highlight the LCP. I thought it'd be really simple. I thought it'd just be either the big SVG in the background or it'd be that entire developer conference string of text. Went down a bit of a rabbit hole. It turns out developer and conference are two separate H1s. And those separate H1s have got fixed widths on them. And this kind of reminds me of the CSS's awesome meme, where the awesome breaks out of the bounding rectangle. There's a fixed width on that H1, which the word conference breaks out of. This then led me down a further rabbit hole, which is, well, how does Google treat this? If the H1 is only the red box wide, but the text is spilling out of it, does it take the rendered text, or does it take the bounding rectangle? Because then that leads to an interesting question. Can we just hack the system? Can we just put a much smaller box around a much bigger bit of text? And maybe Google takes the red box and not the word conference. It turns out the LCP, I managed to work this out because the LCP candidate is this H1, 375 by 140. You multiply that out, and it comes in as much, much smaller. You can tell I put this screenshot in 45 minutes ago because I've not highlighted anything. What happens is Chrome will take the rendered size of the candidate, not the bounding rectangle. So what that means is, if you do the math, and I can't really zoom in very easily on here, I don't think. If you were to try and do the math, you see here the size is 83,000 pixels. 83,000 pixels is much larger than 375 by 140. So what Chrome is doing is it's taking the rendered size of the text. Basically, the bad news is you can't hack LCP by just putting a smaller box around the candidate. So yeah, on the Øredev website, it happens to be an H1. That is the single largest atomic piece of content that is taken into consideration. On my own website, it's an image, but this is actually applied as a background image in CSS. So it's not an image tag, it's a background image. Interestingly, if you look at the meta.com website, we'll find that, again, theirs is an H1. Their LCP candidate is a span of text, not this large image in the background. That's because the large image in the background isn't actually an image at all, it's a video. And as per the spec, LCP does not count video elements for the LCP candidate. This is going to become important later in the talk. But for now, all I need you to know is the type of candidate can change, or it can be different, and the choice of candidate is significant. So your actual LCP element will define how quick or slow you can be. The reason I wanted to give this talk about LCP in particular is because it's my favorite of the core Web Vitals. How sad is that I've got a favorite core Web Vital? What I find quite interesting is LCP is by far the easiest core Web Vital to audit, debug, and fix. But it's the one we struggle with the most. Only 54% of websites on the web, origins, have a good LCP. It's a very, very small number, considering it's the easiest one to debug. So this whole talk is going to be about how can we get that number larger? How can we get that more towards 70 to 90%? So what is good? Good is defined as rendering the largest piece of content within 2.5 seconds. So 2.5 seconds or faster would be considered a good largest contentful paint. That's quite ambitious. When Google defined these thresholds, they didn't just pull the number out of thin air. The number is actually based on quite a lot of research, but it's also based on this, which I find quite interesting. To confirm that a threshold is achievable, we require that at least 10% of origins currently meet that standard. What that basically means is 10% of websites currently manage 2.5 seconds. We think you can as well. That makes it fairly ambitious. Only 10% of origins currently make this at the time they defined the metric, only 10% of websites were achieving it. Does make it quite ambitious. The 2.5 seconds was actually based on other research as well, so there kind of is an inflection point. But what I find interesting is what I infer from this is that in future, if 10% of origins can do 2 seconds, maybe they will update that 2.5 to 2, right? Maybe this number will change. Again, this isn't an SEO talk. Site speed is about way more than just SEO, but if you're in this room learning about LCP, there is a chance that you are worried about rankings. This talk won't go into much detail about that. I've said that already. But SEO is very, very important. But what I want you to remember is SEO gets a customer onto your site, but it's their experience once they are there that dictates whether they will make a purchase or not. And this is a really fascinating case study from just 2 months ago. I was working with a client, and you have heard of them, like specifically anyone, well, we're in Sweden, right? This is a Swedish retailer. You have heard of them. A 500 millisecond improvement in LCP was worth an additional 11.5 million euro a year to this retailer. This has nothing to do with SEO. This is to do with experience on site. And we worked out if we could make it just half a second faster, they would make it an extra 11.5 million euro a year. This is big business, and it's definitely worth paying attention to. So how do we get to good? How do we get to this mythical 2.5 seconds? Well, the whole point of this talk is to get us to that point. And the very first bit of advice I would give you, if you're striving for this 2.5 second LCP, is solve everything beforehand. LCP is what is known as a milestone metric. And in order to get to LCP, largest contentful paint, we have to go through a number of other steps beforehand. Everything on this slide is a potential step that we have to go through before we can get to largest contentful paint. These are all things that I would recommend optimizing in their own right, because if you can get any of these faster, you're going to start eating away at the sort of the delays. The 2 items on there that have asterisks are Google Web Vitals. Google are tracking these as well, but they are not core Web Vitals. So the 2 with asterisks, Google is capturing that information about your website, but is not using that information to rank you. If any of those on that slide are slow, you are already going to be struggling to hit that 2.5 second budget. Here is a really interesting client of mine that I'm about to begin work with. We've got 2.5 seconds to get to LCP. They're already losing 2 seconds to time to first byte. And then from every step onwards, they're losing more and more time until they've way overshot that 2.5 second budget. Solve everything beforehand. That's my first bit of advice. The next bit of advice is actually far simpler. Choose the best element. I mentioned before how the meta site was an H1, my site was a background image. There's a small and finite list of elements that are considered for LCP, and your choice of element will make a big difference. This slide is copied and pasted word for word from the web.dev website, and this slide really, really annoys me, because this is the text they present as, well, it's fact. What they don't tell you, what web.dev don't mention, is that each of these elements has an inherent different behavior. So they're kind of presented as if they're all equal, but some of these are way worse than others. So in no particular order, we've got image elements inside SVG, which are different things. Video elements that have a poster attribute, so that poster attribute, the image, will be considered for LCP. Any element with a background image or any block level element containing text. So it could be a div, a p, an h1, etc. The very first thing to know is that text-based LCPs are always going to be faster. If you can make sure your LCP is a piece of text, you're guaranteed to be faster than any image. Text is faster than images. We know that, right? On the web, text is faster than images. My website, for example, the LCP candidate on mobile is this paragraph element. Running the exact same test with the exact same image over the exact same network conditions, but on desktop, the LCP becomes the image element itself, and we immediately lose 559 milliseconds just because we're picking a different element this time. On mobile, when the image is not the biggest thing in the viewport, LCP comes in at 844 milliseconds. Simply by having an image as the LCP instead, everything's the same. That isn't a responsive image. It totally should be, but I'm lazy. It's not got any different network conditions. It's all the exact same. As soon as we choose an image as our LCP, we lose nearly 600 milliseconds, which is a big proportion of that budget. The caveat is you need to make sure you handle your web fonts correctly, so make sure you're using the correct font display. But it's very easy for me to stand here and tell you, redesign your entire site so that you don't have any images, right? It's not going to work. So let's talk about the use case that affects most of you, which is, what about imagery? What about our LCP when it is an image? I created a very, very simple test case. What I created was a simple HTML file in which I put a render blocking script in the head, and then in the body, I put each of an image in SVG, a poster, and a background image. The reason I put the script in the head is that I wanted to trick the browser. I wanted to force the browser into a scenario where it had to make decisions. Will the browser prioritize the script? Will it prioritize the LCP? Will it do something different? I wanted to try and create some network contention to see how the browser would behave. I knew exactly what I was doing when I sort of created this test. The outcome, though, wasn't exactly what I expected. So I want to step through each of the permutations and tell you which is going to be the fastest. Looking at the data like this, we'll see that an image, 3.1 seconds. Image in SVG is the fastest at 2.6 seconds. A poster image on a video is virtually identical to the image element, so we're looking at 3.1 seconds again. And a background image, 4.4 seconds, it's by far the slowest. One thing I need to point out is that all of these are way over the 2.5 second budget. That's because, just to make the waterfalls really obvious, I made that JavaScript file delay for 2 seconds, just to make the waterfalls really obvious. So for this part of the talk, ignore the 2.5. View these numbers as relative to one another. I made the script delay for 2 seconds purely to exaggerate the results. So don't worry about these being more than 2.5 for now. When I plotted the data visually, I found something very interesting. We've got a problem. Image in SVG reports the LCP completely wrong. It actually reports the paragraph. There is a bug in Chrome at the moment where if you're using image in SVG, it gets ignored for LCP, which means your LCP gets reported way quicker. Chrome is aware of this bug, but if you want to game the system for the next sort of 3 or 4 weeks, you can go and use image in SVG, and it gets completely ignored. When we adjust the data for this bug, we'll find that image in SVG actually goes back to being really quite slow. It's about 4 seconds. So if you look at this lineup of data, we'll see that image in SVG and background image, similar speeds. Image and poster, similar speeds. There are inherent differences in what we use. If we visualize this as a waterfall, certain patterns start to emerge. The really interesting thing I find here is that for image and poster, purple is any image content. For image and poster, the image is actually discovered first, and it's downloaded in parallel to the script. We get complete parallelization, and this is a very healthy-looking waterfall. The browser found the LCP candidate very early and started requesting it in parallel to the JavaScript. Conversely, if we look at image in SVG and background image, we get the exact opposite behavior. The image is not discovered until the moment the script is finished. We completely lose any parallelization, and things get really slow. I'll explain why this is in a second. But for now, we'll look at why image is so good. Hopefully, most of us as web developers will be familiar with image syntax. Image source equals LCP, and that's as simple as it needs. Well, you need your alt attributes, even if they're empty, you need them. Really simple syntax. HTML is really, really fast. We love HTML. Browsers adore this kind of content. The browser is able to find that image very, very early. Despite it being defined second in the page, the browser discovered it first. It's really, this is very, very valuable to us. This is very useful. And the reason this happens is because of something called the preload scanner. Quick show of hands, who has heard of the preload scanner? Like 5 of us, right? We'll go for beers later. For those who haven't, this is it's honestly one of the most elegant bits of design in every modern browser. In the olden days, browsers were very, very slow. There was only one parser, and that one parser was responsible for finding files, requesting files, parsing the DOM, running the file, if it was JavaScript perhaps, doing recalc style, if it was CSS, and things became very heavily serialized. IE8 invented something called the speculative preparser. Because it's Microsoft, they called it speculative preparser, which is like super enterprisey. Everyone else just called it the preload scanner. What this did is it introduced a secondary inert parser that it wasn't responsible for running anything. The secondary inert parser, the preload scanner, just runs ahead in the HTML and starts just putting things in a download queue. It can download things completely separately to how the page is constructed. It's a secondary, inert, asynchronous, download-only parser, which estimates reckon that the web got about 19% faster for everyone just because of this one bit of browser design. And the best bit of news is we don't need to do anything to access it. It just turned on overnight in IE8, and it's been there ever since, and it's in every single modern browser. Basically, the preload scanner can look ahead of the main parser and start downloading stuff. That is how the image was found so quickly. Some resources are visible to the preload scanner, some are not, and this is the entire crux of the problem. Certain files are hidden from this preload scanner. Back in the olden days, waterfall charts looked like the top. Find a file, download it, execute it, look for the next file, find it, download it, execute it, complete serialization. The exact same HTML, but run through a preload scanner, looks like the bottom screenshot, complete parallelization. The preload scanner is one of the most elegant bits of browser design I've personally ever come across. Image in SVG, therefore, is bad, because it turns out images in SVG are hidden from the preload scanner. The preload scanner can't find it. The syntax for image in SVG, it's XML, so it needs the quote, it needs the self-closing tags, but it's also fairly trivial, like fairly simple syntax. The problem is that is hidden from the preload scanner. If you copy and paste that into an HTML file, the preload scanner cannot find that image reference. That's why your waterfall looks like this. The browser has to run the JavaScript before it can parse the rest of the HTML, which means it doesn't find the image in SVG until the very last moment. Way too late. The browser only found the image when it was about to render the image, which is like completely inappropriate. That's way too late to be finding stuff. So, image in SVG is hidden from the preload scanner. I'm not entirely sure why. I presume, and this is just a guess, I'm guessing that Chrome has a second style of parser for SVG embedded in HTML, and the preload scanner that works over HTML skips over any SVG content. That's just a guess. Statistically, it's very unlikely you are using this element. Less than 1% of the web uses this as its LCP, but it's just nice to be aware of. Poster is good. This was a very pleasant surprise for me. Poster images on videos are a really good candidate. They're very, very fast. The syntax is simply a poster attribute on the video element itself. And it behaves the exact same as image. It's available to the preload scanner. The browser finds it really, really early. It downloads it in parallel to the JavaScript file. This is a very pleasant surprise. So poster behaves like image, is available to the preload scanner, but I have some slightly concerning news. Currently, Chrome does not consider the first frame of a video for your LCP. What that means is if you have a video with no poster image, it will go and use a piece of text instead, perhaps, much like the meta.com example. If you put a poster image on your video, then it will start to use that as your LCP. There is a rumor, there are murmurings, that Chrome may start taking the first frame of a video if you don't use poster images. And this is bad news because text is really fast, images are slower, videos are much slower. If you are using video on your site currently, prepare for this change, start using poster images, because there is a potential, actually it seems like quite a high chance, that what's going to happen is Chrome will start taking the first frame of your video as the LCP if you don't use a poster image. So my advice here is start using poster images just so you can be a little bit faster. If you're wondering, well, I found out only this week, well, Tuesday, isn't it? So last week. You've got YouTube to thank for this. YouTube were rebuilding their video player, and they realized that poster images didn't really work for them. If you go to an auto-playing video and they show you a poster image, and then it flicks from like the poster to the actual video itself, they thought that was a really bad user experience. If you link to an auto-playing YouTube video, you'll notice that they show you a blank screen and then start playing. So YouTube decided, poster images don't really work for us, so we don't like the poster element, so we're going to ask Chrome to start using the first frame of a video instead. Like, cheers, YouTube, thank you. So it's their fault. Similarly to image in SVG, background image is also a pretty bad idea, and this is because of just how CSS works. The way CSS works is inherently very slow. What I did is I just put an inline style on the div in question. I didn't use an external style sheet because that would have definitely been slower. That would have been a bad experiment. Simple inline style on the div in question led to a waterfall that looks like this. What we'll see here is that we've lost any parallelization. The image is not discovered until the moment the JavaScript is finished. This is very, very slow and looks exactly like the image in SVG example. I expected this to happen because of how CSS works. I knew this was going to happen. Background image is hidden from the preload scanner because background images and web fonts are late discovered resources. If you had a CSS file that had 1,000 background images in it, but the page only needed one of them, you know the browser is only going to download the image it needs. That's sensible, it's defensive. The problem is the browser doesn't know it needs the image until it's about to render the DOM node that needs it. So this is like this like tug of war. The browser needs to be conservative, but also needs to be fast, and it can't really reconcile the two. So web fonts and background images aren't actually requested by your CSS at all. In fact, CSS does not download background images. The render tree does. So this is a really interesting paradigm where it's not until the browser spots a DOM node that needs that background image that it will dispatch the request. This is where things become really interesting. What this means is CSS is not your bottleneck for background images or web fonts. Your DOM is. If it takes you a long time to get to painting a DOM node that needs a web font or a background image, that's when the browser will dispatch that request. It does not matter how fast your CSS is. Your CSS doesn't download that image. It's the DOM node that requires it. So actually, probably your HTML is a much bigger bottleneck than your CSS when it comes to optimizing background image performance. Yeah, here we go. So background images are slow because they aren't requested until the browser is ready to paint the DOM node that needs it. So key takeaways here, not all candidates are born equal. Your choice of LCP element will impact how fast or slow you can be. But don't worry, if you're using background images, we can hack around it. If you're using image tags, we can make them even faster. The next bit of the talk is all going to be about how to optimize these further, regardless of what choice you made. So my day-to-day is working with development teams and organizations to help fix site speed issues. And when I'm optimizing LCP, a lot of the things I come up against are actually mistakes, things where the developers kind of shot themselves in the foot, and it's kind of upsetting to see, but they are quite easy to fix. The next section of the talk, I want to look at some common mistakes that developers make, and sort of they work against themselves, work against the grain. The first one is like just a massive, this one used to really upset me, now it just frustrates me. Don't lazy load your LCP, right? If lazy loading, yeah, sure, it makes your website faster by making your images slower. And if you make your main image slower, expect bad LCP times. Looking at the HTTP archive, I found that almost 10% of websites use native lazy loading. A further 5 to 6% use a JavaScript implementation of lazy load, which is even slower still. It's a really common pattern that I see, and it's usually, I mean, the reason this became so prevalent is people would be using like WordPress plugins that would automatically magically make their site faster. And what that would do is just go through the entire site and put loading equals lazy on any image tag it found, including images that are in the viewport. Very naive sort of optimization that actually was very harmful. So yeah, this is the syntax for lazy loading. Very, very simple. Make sure this is not on your LCP. I get a question from a lot of developers, and it's a very well-meaning and actually quite intelligent question. Can't we just add loading lazy to every image, and the browser then decides if it needs it or not? Because the whole point of this attribute, loading equals lazy, is the browser makes its own mind up. Well, it's in the viewport, I won't lazy load it. This one is below the fold, I will lazy load it. This is a pretty sensible question. However, it's not as simple as that, because one, again, very elegant bit of browser design, the moment you put loading equals lazy onto an image, it hides it from the preload scanner. It turns the preload scanner off. So we get back to square one. It's almost like having a background image. I think this is, again, a very elegant bit of design. At the top is just a regular image tag. The bottom is that image tag as soon as we put loading equals lazy on it. This is a very destructive, very harmful behavior if it's applied in the wrong place. One thing I tend to do, I've got a little debug style sheet that I enable. I just put this in a debug style sheet and click around my client websites. What this is going to do is throw a red border around any image that's got loading equals lazy, and all I do is click around the site, and any red image above the fold is a problem, and that becomes our little list of things to fix. On the Economist website, you can see these two images were lazy loaded. A simple task for the Economist is going to be remove the attribute for above the fold images. The next one, don't build your LCP in JavaScript. This is a very broad church. This covers quite a lot of things. JavaScript is the fastest way to build a slow website, right? That's probably a very controversial thing to say, but just JavaScript is it's a slow path. Avoid JavaScript wherever possible. I was working with iPlayer. They're sort of like a British Netflix video platform, and their site was all server rendered, apart from this one main component. The actual video player itself was built on the client. So the whole page was server rendered except for this bit. It was all built on the client, which meant they had to download an app.js, which had to boot, which then hydrated this, which then put an image tag in the DOM, which then requested an image, which is just a really slow way of doing things. The waterfall looked like this. What we'll see is that the app.js, this kind of an odd slide setup, because that's going to look really tiny to you all, I'm afraid. But what you'll see is the image isn't requested until really, really late. It's, if I look at my screen, it's the 43rd request, which is way too late. I set the developers a simple task of just rebuild this so it is server rendered way, way, way faster. It went from being the 43rd request to the 17th, which still isn't great. There was a lot more to optimize as well, including this thing here, which we'll come back around to. But you can see the day they deployed this change. Hopefully you can see it. It's fairly obvious to me. They deployed this change, and things got markedly faster. In fact, it was a 43% improvement, and it took them about 90 minutes just to make sure this component was server rendered, not built on the client, way, way faster. So that little bit I talked about, the further optimization, was because they were hosting their LCP image on a different origin. Don't host your LCP off-site. The actual best example I've got of this was me about 3 weeks ago. I accidentally nudged my LCP image onto Cloudinary. So Cloudinary is an amazing service for optimizing images on the fly. Very, very powerful, very, very effective. But the problem is that image now lives on a different domain, and trips to different domains incur latency, right? Network negotiation. And you can quite clearly see when I had this accidental sort of like kind of regression deployed. What you'll notice is I went from 2.1 second LCP to 3.5. That is taking me way over that 2.5 second budget. What I find really interesting about this from like more of a philosophical point of view is an unoptimized image hosted on the same domain is faster than an optimized image, right? Which is weird, right? The image was 1.5 times smaller but took 2.6 times longer to display. That's a really stark contrast. Self-hosting an unoptimized image is faster than externally hosting an optimized one. Of course, I optimized the image and self-hosted it. Actually, this is really lazy. What I did is I hosted it on Cloudinary for a few days by accident, but then did right-click Save As, moved it back onto my own origin, and I got both. Don't usurp your LCP. This is a piece of shit slide because I couldn't think of a better word than usurp. It's such an archaic word. Usurp means kind of like undermine or like overrule or dethrone. Don't dethrone your LCP. This is something that really does break my heart every time I see this. Developers may build a page that they believe to be fast, but then third parties and tag managers and all this kind of stuff kicks in, and something steals their LCP away from them. This was a really interesting case study from REI, a big retailer in the US. This is quite a noisy slide, so I'm going to talk you through it. On the left is day one. On the very right is day two, and in the middle is a visual diff of the page between day one and day two. What you'll notice is at the bottom, we've got a 54% increase in LCP, 54% difference. That's huge. I'm going to leave this here for a second and see if any of you can work out what happened. This is why monitoring is so important, because none of the developers spotted this themselves. Because on your dev site, you probably don't have your consent forms or your consent managers. You don't have tag manager. You don't have ads. So your dev site, not only is it from localhost, so it feels fast, it's also a very different environment to what your customers experience. None of the engineers at this company had the cookie banner popping up when they were working on their dev sites. So what happened is, on day one, the H1 said Cannondale full suspension mountain bikes. They sold out. They sold the last, if you look, I don't know if you can really see it, if you're in the front row maybe, it says one product. They had one Cannondale mountain bike left in stock. They sold it. So on day two, the CMS, intelligent bit of e-commerce platform here, said, well, you can't buy a Cannondale mountain bike anymore. Let's send you to the mountain bikes page. The H1 got a lot shorter. So on day one, the H1 was 46,000 square pixels, which is bigger than the consent banner, which is 44,000 square pixels. On day two, the H1 was much shorter, 33,000 square pixels. The cookie banner, which loads after everything else, was now the biggest element on the page. Cookie banners that are late loaded is really annoying because the H1 loaded at whatever time. And then a new larger element appeared that none of the developers saw because it doesn't pop in on their development machines. This is why monitoring is so important. It really breaks my heart when a developer does a really good job to build a page a certain way, and then your cookie banner arrives and steals it away from you. Or like when marketing put a big sign up to our newsletter and it's got a huge image in it, and the newsletter sign up that annoys you just as much as your customers, just one person in marketing think it's a great idea, steals your LCP away from you. So be really careful about this and make sure you've got monitoring in place that can spot these regressions. Right, those are just some common mistakes. There are way more, but these are the most important and probably easiest to diagnose. The next thing I want to talk about is stretch goals. What are things we can do to actively go ahead of the curve and sort of overachieve in a way? So I want to look at some stretch goals, some interesting new APIs we can use to get things even faster. The very first thing I want to talk about, you may have probably already used because they've been around for quite a while now. The first thing I want to talk about is resource hints. If you've ever used a pre-connect or preload, right, link rel equals preload, for example, that's a resource hint. These are quite commonplace. They are a bit of an anti-pattern, so go easy with these. In fact, everything I'm about to talk about from here on in, go easy and test everything. But the syntax is really straightforward. It's a declarative fetch, in this case for an image called lcp.jpg. These usually, but not always, live in the head of the document. And this just tells the browser, hey, look, you don't know it yet, but you're about to need lcp.jpg. It's a queue jump. It allows the browser to discover things that it otherwise would find quite late. In fact, there's a clue in the name. The preload, link rel equals preload is a good way to reintroduce hidden files to the preload scanner. So background images, I mentioned, are hidden from the preload scanner. We could use link rel equals preload to reintroduce them. Same with image in SVG if you're like one of 3 websites on the planet that are using that. You could use preload to reintroduce them. So like I say, very useful if your LCP candidate is a background image. My own website uses a background image for its largest contentful paint element, and the before and after is really quite striking. There's some really interesting stuff in these next waterfalls. It's nice to write your own reviews, isn't it? I just told you my talk's interesting. This is fascinating, though. I loved seeing this. So the top screenshot is my website using a background image with no preload. You'll see here that the image, the big purple bit, is the 4th request. It's requested from the body tags. And here's a real pro tip for anybody who looks at waterfalls. A great pro tip for any Blink or Chromium-based browser is Chromium it loads web pages in 2 phases. The first thing it does is your head tags, because they're really important. Your head tags are render blocking. It's the most important part of the document when it comes to start render. So Chrome will load your head tags separately to your body. So what you can see here is, in the very first screenshot, the only thing I've got in the head tag is one CSS file. It's orphaned. So Chrome will do the head tags first, then you'll see almost a break, a natural break in the waterfall, and then all of a sudden, boom, it's your body tags. What you'll see here is that image is loaded from the body phase. The image took 932 milliseconds. The reason it took 932 milliseconds is because lots of other files are downloading at the same time. The bandwidth that's available to Chrome is getting shared across those files. So some bandwidth goes to the image, then some goes to the document, then some goes to a JavaScript file, then it comes back to the image. If you look at the purple bars, any light purple is the file just waiting on the server. It's effectively time to first byte. Dark purple is we are sending data. So what you'll see is that Chrome actually just receives a bit of image data, then receives a bit of JavaScript, then document, then more image. It takes 932 milliseconds. The moment we preload that file, we'll see that it comes up to being the third request rather than the fourth. It's requested from the head part of the document. You see it's now in parallel to the CSS, but the dark purple is now pretty much unbroken. Because it's being loaded from the head part of the document, it's treated as far more significant. So all the bandwidth goes to that image and that image alone, which means it took 445 milliseconds to download. The image is the exact same size, the exact same number of kilobytes, but because it got exclusive access to the bandwidth, it downloaded twice as fast, which led to a 1.2 second improvement in LTP. Now, this probably sounds wonderful and really powerful, but please don't start implementing preload until you go and read this. There are problems with preload. There are some bugs in Chrome where preload can technically, in certain cases, make your website slower. A client of mine this morning, I need to go and check the actual results, they just deployed a release in which we turned preload back off because it was making their website slower. So if you want to implement this, please be aware of the caveats. The next thing is priority hints. I'm completely smitten with priority hints at the moment. They're very, very powerful and, again, very, very simple. They have a similar feature or similar kind of use case to preload. It's basically to encourage a faster fetch. The syntax, again, very, very simple. It's a declarative fetch, but this time it attaches to a certain element. This instance, it's attached to an image element. Normally, but not always, you will find these in the body tags. So fetch priority equals high just encourages a faster fetch for the relevant file. This is useful for in-page resources. So preload is useful for like CSS resources. Fetch priority is useful for in-page resources. This is great if your LCP candidate is an image tag. What this does is it allows us to influence priorities. And in order to understand what that means, we need to understand what priorities are. When we load a web page, and this is true of every single browser, not just Chrome, when we load a web page, each file is assigned an inherent priority. And that priority is a mixture of things. Where in the HTML was it defined? Was it defined in the head or in the body? Was it defined early or late? Does it block rendering, yes or no? And each of these sort of heuristics come together to form a priority. And we've got very little influence over what these priorities actually are. That is until the Priority Hints API was launched. We now get we can influence these no end. We can go in and change things. If you've ever looked at much performance optimization work in web page test, you may have seen something like this in the past. This is the LCP image, and it's got an initial priority set to low. Basically, every single image is assigned low priority because they don't block rendering. They're completely asynchronous. However, if Chrome realizes the image is in the viewport, it can change the priority. So you'll see that initial priority was low, but then as soon as the browser knew this was going to be in the viewport, the priority it was requested with switched to high. This is smart, but it's not good enough because it didn't know it was high priority until the moment it was dispatching the request, which is, again, way too late. I'm about to show you a screen recording, and I want you to pay very close attention to the middle of this red circle. Image, low priority, low, 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 and then high. That's that behavior in action. That image was queued up for 2.16 seconds. I'll just pull this out into a static screenshot. 2.16 seconds, the browser knew the image existed, but just didn't do anything. It was like, cool, there's an image, I'll get around to that. Then when the browser realized that, oh shit, this was the LCP, it chases it up with a high priority request, but it still left that image sat there for 2.16 seconds. When you remember that we've only got 2.5 seconds to play with, losing 2.16 to nothing at all is a terrifying prospect. That led to an LCP event of 13.8 seconds, which is just way too bad. That's nowhere near good enough. I added one simple attribute value pair to this image tag. I want you to watch that red circle again. Very, very, very stark difference. We'll pull this out into a static screenshot. That was queuing for 0.85 milliseconds. Put it another way, that was over 2,000 times faster. For the sake of one attribute, 2,000 times faster. Oh, by the way, if you're a consultant or a freelancer, never tell your clients what you actually did, because I can't submit an invoice for that. Hey, I put an attribute on your image. Can I have 10,000 euro, please? tell them the outcome of what you did, especially saying things like, I wouldn't even tell them I saved you nearly 2 seconds. I'd be like, it was 2,000 times faster. But yeah, that's huge. The outcome there is staggering for the sake of one attribute value pair. That now got us an LCP down at 4.9 seconds, which is still way too late. But the amount we just clawed back for the sake of one little attribute is astounding. The key takeaways here are we took back almost 100% of that queuing time, right? As a percentage, it's just mind-blowing. And LCP, we improved by nearly 9 seconds for the sake of one little attribute. So I'd really encourage you to start experimenting with fetch priority for your LCP candidates. Just as a complete aside, because I think I've got time, fetch priority low, a good candidate for that would be things like the Facebook tracking JavaScript thing that is asynchronous, but also really not important to the user experience. You could use fetch priority low for things that are like, yeah, do you know what? It'll be nice to have, but fetch it with low priority. Things like your service worker that doesn't install until like the page is loaded anyway. Fetch priority low is really good for things that you want to execute, but you will completely happily admit they are not important to the user experience. That would be a use case for fetch priority low. The last new feature I want to talk to you about is image decoding, and this is very, very new. It's also not very well documented, which means it isn't very well used or widely used. When you read the spec, it doesn't really tell you how and when to use this feature. It's very, non-committal, which really annoys me because it doesn't give developers any insight or practical advice. The closest you get to advice is the spec simply says image decoding is said to be synchronous if it prevents presentation of other content until it's finished. Now, reading this, I see the word prevents, and I think, oh, this sounds like a bad feature. The word prevents isn't really good vibes, right? I don't want to prevent anything. But when you think about it, maybe this is useful if we prevent other content in favor of the image. So I made a simple demo, a simple test case. What decoding will do is it will tell the browser whether to atomically render an image or not. Should it block other content or not? Decoding equals async is the one we don't want to use. What I want to do is start with the bad one first and show you the gains we can get. If we tell a browser to asynchronously decode an image, we get a very interesting pattern of work. Again, I fear that people sat a little further back might struggle with this slide, but what we've got here is a trace of a simple, the exact same demos that I made previously. We've got a simple trace here. What we'll see is the very first frame, we are just beginning to render an image. If I can try and zoom in on this for you. You see there's a thin sliver of image just under the H1. We began decoding the image. The second frame, we did paint a new frame to screen, but there's no more image data. We painted a visual update, but it wasn't the image. What actually happened was there are 1,000 paragraphs below the fold, and the browser is currently rendering those. Because we told the browser, hey, asynchronously decode the image, do other things in between. The third and final frame is a fully decoded image. So it took 3 steps to show this image. In the meantime, we had this recalc style and layout task, which is the browser actually rendering off-screen paragraphs. That's not useful for the user experience or for the LCP metric. The overall time here was 700 milliseconds. 700 milliseconds to, and bearing in mind, we've only got a 2,500 millisecond budget. Losing 700 of them to decoding the image is a big, big chunk to lose. So if we switch this to decoding equals sync, the important thing to tell you here is the browser won't decode the image any faster. What it will do is it will only decode the image. It won't sneak any other tasks in between. So now the exact same demo, we see the first frame, we're beginning to decode the image. The second frame, the image is fully decoded. There is no third step. There is also no layout or recalc style task. We aren't rendering any of those off-screen paragraphs. And the overall time now is over 2 times faster. It's now 320 milliseconds overall. So one pattern I'm beginning to recommend to developers and to my clients is any candidate that could take fetch priority high, complement it with decoding equals sync. Tell the browser, look, don't bother rendering content around this image until you finish the image itself. Conversely, you may want to try this. Every time you put loading equals lazy, you might want to put decoding equals async, because there's no point holding up CPU cycles for rendering an image that is off-screen. So I went through a lot of stuff there really quite quickly. I'm going to try and summarize this in one slide. Basically, LTP is the final metric. If you're struggling with LTP, make sure you're auditing things like time to first byte, start render, etc. LTP is kind of the final metric. Solve everything beforehand. Choose the best candidate. Text is the best candidate possible. Failing that, image is probably the second best. The reason image is so good, I've said previously how image and poster behave almost identically. The reason we would prefer image is because we can put decoding equals sync on image attributes. We can put fetch priority high on image elements, and fetch priority on image elements. You can't put fetch priority on a video or its poster attribute, and you can't put decoding equals sync on a poster image. So image tags, they can take the extra attributes, makes them even nicer. Expose the LTP candidate early. Don't build your websites in JavaScript, especially don't build your LTP in JavaScript. Don't make silly mistakes. Lean on these new APIs. There are new tools and APIs we can use. But as with everything, always, always, always test. I whizzed through that fairly quickly. I want to thank you for your time and your patience. I think we're doing questions, so if anyone has any questions, I'll take them now. But yeah, I just want to say thank you all for listening.